So, looking at review topic 4, questions from data, questions from tables. So let's look at number 1. Use the data. Well, let me read the question, I guess, so we get a feel for what's going on here. The height of a tree is given by a twice differentiable function h. So that means we could take a first derivative and a second derivative. That means it's continuous, it's smooth, there's nothing crazy going on. And that makes sense. Like the height of a tree doesn't, jump or have asymptotes or anything like that. So twice differentiable. Selected values of h are given in the table. Question A. Use the data in the table to estimate h prime at 6. Using correct units, interpret the meaning of h prime at 6 in the context of the problem. Okay, h prime, that's a derivative, but it said approximate it, which I think makes sense because I don't have an equation, so I can't exactly tell you what h prime is. So how am I going to approximate h prime of 6? With the data, yes. How am I going to do that? Yeah, algebra slope. y2 minus y1 over x2 minus x1. Or I guess h2 minus h1 over t2 minus t1. Because that would be an approximate derivative. I got a lot of choices for t's and h's, though. Probably the one between 5 and 7 would be the best choice. So 11 minus 6 over 7 minus 5. And let's put units on there because that will help us interpret the answer. H is in meters and T is in years. So 5 over 2 meters per years. Using correct units, got it. Interpret the meaning of h prime in the context of the problem. So what is 5 halves meters per year? What's that mean? Yeah. Is how much or how fast or the rate, probably be even best to use the R word, is how fast the tree is growing. And it made a big deal out of units, so let's go ahead and throw it in there. In meters per year at the 6th year. That's probably only a two-point part of that problem is my guess. Because it has 4 parts and that one was pretty easy. Part B, explain why there must be at least one time between 2 and 10 such that h prime equals 2. H prime equals 2 between 2 and 10. Somehow. Any thoughts on that one? Well, this slope was 2.5. Maybe we find all the slopes and see what we learn? Because we're saying the slope is equal to 2 sometime in there. So this slope would be 4 over 3. This slope would be 4 over 2, which would be 2, which is kind of what I was looking for. And then lastly, this slope would be 0.5 over 1 or 0.5. Okay, but those are approximations. Those aren't exactly right. But there is a 2 sitting right there. So, I can't just circle that and say, hey, there's a 2. Must be it. Let's see. from t equals 3 to t equals 5, the average rate of change is 2. Right? That's also what we found in part A, was the average rate of change. But what they were talking about is the instantaneous rate of change. So, hey, what's that thing that says that the instantaneous rate of change equals the average rate of change? What's that thing called? MVT, by the mean value theorem. The instantaneous rate of change equals the average rate of change. So that means that the average rate of change is 2. So the instantaneous rate of change equals 2. Somewhere, not just between 2 and 10, but somewhere between 3 and 5. We can give a little more specific answer. And they were explicitly looking for you to say MVT right there. The mean value theorem. And that was tricky because they didn't say use the mean value theorem. They asked a question that required you to know the mean value theorem. My guess is that's probably where 2. Use a trapezoidal sum with 4 subintervals indicated by the data in the table to approximate the average height of the tree. Okay, well, before we jump in with trapezoidal sums, let's make sure we know what average height is. The average height. I think we hit that yesterday or day before, something. 1 over b minus a times the integral from a to b of whatever function we're dealing with. That's the average height. But it said use a trapezoidal sum because I won't be able to get this exactly. I will use a trapezoidal sum to estimate that. And my guess is a whole bunch of people are going to do the trapezoid rule, because that's not too bad, but forget to divide by b minus a. So 1 over 10 minus 2, and then the trapezoid. Just add up the trapezoids. So a trapezoid is the width of the interval times the average height. I think there's other formulas, but that would just be the way to go. So the width of the interval is 1. The average height is 2 plus 1.5 over 2. That's the first interval. The second interval from 3 to 5 has a width of 2. Average height, 2 plus 6 over 2. Next interval is also 2 wide from 5 to 7. 11 plus 6 over 2. And the last interval is 3 wide. Average height of 11 plus 15 over 2. And this was a no calculator question. So definite safe stop on that. Like, I'm not messing with that. Like, that's fine. That's good. I'm not at all going to mess with that. I mean, I could, because it's just adding and multiplying, but why bother? Like, I got other things to do, other pieces of this problem to solve. Maybe if I had a calculator, maybe I'd take a little time to get what the answer is. Because if you did take the time, you could make sense of your answer. Like, just looking at these heights, it goes from 1.5 to 15. So I don't know, if I'm guessing, maybe the average height is 8-ish. 7, 8, 9, somewhere in there. So I have a pretty good idea what my answer should be, but I really don't know if this is in that range or not unless I actually do it. But I don't have time to do it, so I'll leave it alone. Part D. That might be 2 points as well, because one for the formula and one for actually typing everything out. The height of the tree in meters can be modeled by the function g of x equals 100x over 1 plus x, where x is the diameter of the base of the tree in meters. Okay, so the height is g, but x is the diameter. Okay, so this is height not as a function of time, like we were kind of just looking at, but height as a function of diameter. When the tree is 50 meters tall, I'm going to translate to variables we're using. So when g is 50, the diameter is increasing at a rate, so dx dt is 0.03 meters per year. I think I see a related rates problem coming. According to this model, what is the rate of the change of the height of the tree with respect to time? So that's a mouthful, but that's find dg dt when g is 50. Ugh. Yuck. So I need to take a derivative of this thing with respect to t. So I'm headed toward quotient rule there. So f prime would be 100, but 100 dx dt, because x is changing. So we don't usually have a x, or a chain rule when x is involved, but x is changing, so I need a dx dt on that. What about g prime? What will g prime equal? Dx dt. Okay, so at least those pieces aren't bad. I mean, I still got to do the quotient rule, but the individual derivatives are easy. So let's see, g f prime, g f prime minus f g prime all over g squared. All right, let's see. I know dx dt, but I don't know x. That's kind of annoying. How can I find x? So what do I know? What would help me find x? Yeah, 50 can go in for g. So 50 plus 50x equals 100x. Oh, they did us a favor here, didn't they? 50 equals 50x. X equals 1. Well, that was nice of them. And this was a calculator question, so they didn't have to be... No, this was no calculator. So I expect nice answers with the no calculator problems. So now I know everybody This is going to be another safe stop here. 1 plus 1 times 100 times 0.03. I'm just filling in pieces now. 100 times 1 times 0.03 all over. Oh, let's just be obnoxious about it and leave it as 1 plus 1 squared. Figure it out. Done. Yep. Passive-aggressive note to grader. You figure it out. I'm done. Actually, let me reread the question to make sure I'm done. What is the rate of change of the height of the tree with respect to time, dg dt, in meters per year? I think we're just going to trust that all the units work out because I don't want to take the time to make sure. So there's my answer. Yeah, I'm done. That's probably a 3-point problem. Split up somewhere in there. So, again, 9 points on that problem. Could you get all 9?
Nope.
Maybe not. Could you get 5 of them or 6 of them? Hope so. Hope so. Number 2.
Oh, there's a second problem.
There's a second problem.
What's the giveaway once you get 100 subscribers?
First period put that up there. That's, yeah, sorry.
Man.
I need to erase it. Number 2. Okay, this is a calculator one. So I suspect the numbers won't be pretty on this one. In fact, you can kind of see that already. We got more decimals going on here. But it also means I can use the calculator to evaluate derivatives and integrals and all that good stuff. So, by the time you get to this point in the class, you realize that maybe the no calculator questions are the preferred ones because they don't, the math is easier, or at least it's only calculus. It's not crazy computational stuff. Let's see. A tank has a height of 10 feet. The area of the horizontal cross-section of the tank at height h is given by the function a, where a is measured in square feet. The function a is continuous and decreases as h increases. Selected value for a given in the table. So I've got some kind of tank that gets smaller as we go up. I don't want to try to guess the shape of this tank, but at height 0, that cross-sectional area, and I don't know that it's a circle, but it's getting smaller. At h equals 10, the cross-sectional area was 2.9. So I'm just trying to visualize this thing. And as soon as I see a table, I'm guessing some kind of Riemann sum is coming. Left, right, midpoint, trapezoid, something's coming. Use a left Riemann sum with 3 subintervals to approximate the volume of the tank. Okay, so I'm going to area times height would give me volume. So my volume is going to be approximated. And it even told me to use 3 subintervals. So Riemann sum, that's just rectangles. So trapezoid's kind of tricky. Riemann sum is just adding up the rectangles. So the first one is 2 wide. Which height will I use? Yes. The next one is 3 wide. And again, the left sum, 14.4. And then 5 wide. And the left height is 6.5. And you are free to leave that as well. I mean, it's a calculator problem, but safe stops are still fine. it does say indicate units of measure. Well, there's a couple ways to do that. What are the units of measure for volume? What's a volume unit of measure? Cubed. So I know it's going to be feet cubed. But you could figure that out from here, because that's 2 feet wide and the area is feet squared. So maybe that helps make sense. It's feet cubed. And again, you got a calculator, but meh. Part B, does the approximation overestimate or underestimate the volume of the tank? Explain your reasoning. Let's see. The area is decreasing as h increases. We don't really know what it looks like, but it's going down. So if we use a left Riemann sum, yeah, that's going to be an overestimate. But explain. How do you know? Okay, but it looks like over isn't a calculus reason.
I drew it. It goes above the graph.
Okay, the function is decreasing, or area is decreasing, and we're going from the left. That's all you need to say. Area is decreasing, and we used a left Riemann sum. So the combination of those two things means we got an overestimate. So yeah, you looked at it and you knew it, but describe what you were looking at. You were looking at a decreasing function and a left sum, which meant you were going to get an overestimate.
If I drew this graph, is the grader not smart enough to realize that that's my reasoning?
They are, but you're probably going to get 1 point for saying overestimate and 1 for the reason. So they need you to use the calculus words.
That's a lot of work.
Graders aren't mind readers. You probably don't want them to be mind readers, right? What are you thinking about when they're grading your test? Part C, the area in square feet is modeled by the function. All right, I'm glad we got a calculator for this, because I don't know what's going on here. Based on this model, find the volume of the tank. So that's the area as a function of height. So how can I find the volume of the tank? This is tricky.
Give it a wild guess. Plug it into the calculator.
Plug what into the calculator? What'd you say?
I said
Integral. Integral. It's very much related to what we did in part A. And then maybe that's why they ask it in that order. Because we estimated the volume by doing a Riemann sum, which gives us an approximation of the integral. And now we can just find the actual integral. 0 to 10. F of h is already defined, so I don't need to rewrite it. In fact, that's the only work I need to show. I can let the calculator go from there. Yeah, that's not a safe stop though, because that's still calculus left to go. I'm not going to put this in for y1 because I don't think I'm going to need it again. So I'm just going to type it in here. Oh, feeling fancy with the fraction bar as well. I had to think a little bit on that one. Always 3 decimal places. one for that and one for that. My guess. And again, that's all the work you have to show. Like, they know what you're doing. They just wanted you to know that to find the volume, you would integrate. Part D, water is pumped into the tank. Okay. When h equals 5, the height is increasing at a rate, oh, here we go, related rates, dh dt is 0.26 when h is 5, dh dt is 0.26 feet per minute. Using the model from part C, so we are going to have to use that equation. Find the rate at which the volume of water is changing with respect to time. Find dV dt when the height of the water is 5 feet. Indicate units of measure. I could get units of measure right now. And if it's worth a point, I might could put it down and get a point. So the units is going to be, what is the units going to be for dV dt? Feet cubed per minute. It's possible that that's worth 1 point since they specifically said indicate units of measure. So you might get a cheap one there even if you can't figure out anything else. Hopefully you do. Alright, so I need dV dt. Well, we said v was the integral from 0 to, I'm going to switch it to h. F of, I need like a filler variable because I got too many h's here, so I'm going to call it f of x dx. Oh, I see what's coming. That's v, related to problem part C. Now I want to take a derivative of that. So dV dt equals, what about on the right hand side? What's the derivative of an integral? Well, be careful. F of h, because remember we plug in the top thing. That's not quite it yet. That's close. Do you remember when we took a derivative and it was like 0 to x cubed? What we would have to do? We would have to chain rule that thing. Times h prime or times dh dt, which I was expecting to have to use because they gave me dh dt earlier. Not a safe stop. So dV dt, f of h we already have. So f of, well, when h equals 5, f of 5, dh dt they gave us, 0.26. Still not a safe stop because I have to do the evaluating. I have to plug it in. I could safe stop if I wanted to just plug in 5. I could safe stop that right there. That would be okay. We already said it was feet cubed per minute. I mean, you have a calculator, so you can find it, but even so, that's a safe stop. It's calculator ready. Hello, Mr. Grader. If you want to find it, you find it. I'm not interested right now. All right, so table problems. Almost always have a Riemann sum or a trapezoid rule associated with them. So your assignment today is the next two, number 3 and 4. Same type stuff. One more week of good practicing, and then you'll be ready.